Hey, physics students. I want to give you some notes here about two things, Newton's third law and the force of gravity, putting numbers on that so we can start to move toward putting some numbers into our force diagrams. So let's talk about Newton's third law first. Newton's third law is out there in the world as one of these little things that people think they know about physics or they've heard. This is the equal opposite force. But the way that it's out there in the world, for every action there's an equal and opposite reaction. That's a pretty lousy way of saying and trying to understand what Newton's third law really is. This is how we're going to understand it. By definition, what's a force? A force, you have this somewhere else in your notes, this is not new, an interaction between two objects. Could be a baseball bat and a baseball. Could be your hand and your friend's hand as you give each other a high five back in the days when we were allowed to give each other high fives. So a force is an interaction between two objects. It could be like the Earth and the Sun. There's a gravitational interaction between those two objects. So any two objects, if they're interacting with each other, there's a force associated with that. All right, so since the rest of Newton's third law kind of just comes right out of this definition, it just is a logical extension of this definition of force. If a force is an interaction between two objects, there's only one force, right? The force is the interaction between the two objects. So therefore, object 1 and object 2 experience the same amount of force but in opposite directions. So, in other words, if you have two things pressing against each other, like this dry erase marker and my hand, then the force, there's only one force here. The force is the interaction between the palm of my hand and the dry erase marker. There's only one interaction. So it's not possible that my hand could be experiencing a different amount of force than the dry erase marker is. So how much force is there? Well, I don't know what number. I don't know how to put a number on that right now, but I do know that the marker is experiencing a force this way from my hand on marker, and my hand is experiencing a force this way from the marker. And whatever that number is, when we can finally put a number on it someday, it's exactly the same number. It can't be different. Now that's pretty easy to understand when you got two things pushing against each other and that there's no motion. It's harder for people to understand, but you're going to try real hard, that this is always true. So for example, if you're watching a baseball game and you see that baseball moving in toward home plate, and then batter swings the bat and it hits the baseball, and let's just say for fun that baseball player hits a home run. So while the ball is in contact with the bat, what's bigger, the force of the bat on the ball or the force of the ball on the bat? Think about that for a second. The answer is they're exactly the same because there's only one bat-ball interaction. So it's not possible that somehow like the bat could be like touching the ball harder than the ball is touching the bat. They're touching each other. There's only one touching, and that's like reciprocal. You can't have a different amount of interaction for one of them versus the other one. So then you might think, well, that doesn't make any sense because the ball's going to go flying over the, 400 feet over the wall in the back, and the bat is like going to actually keep moving forward. So like, how does that make any sense? Well, there's other forces acting on the bat, right? The batter's swinging the bat, and the difference, it's not like the only force acting on each one of those is the bat-ball interaction. But that bat-ball interaction, it cannot be different for the two objects. Here's another example. The Earth, as you might know, unless you're like one of these nut job flat earther types, the Earth is going around the sun. That's a fact. And why is it going around the sun? Well, the sun is much larger than the Earth, about 1 million times bigger, and there's a gravitational attraction there's like a pull on the Earth from the sun. So here's a question for you. So there's a force, right? So what's bigger, the pull that the sun exerts on the Earth because of gravity, or the pull that the Earth exerts on the sun because of gravity? I bet you see the answer coming, don't you? You know what it's going to be? They're exactly the same. There's only one Earth-Sun interaction. They're locked together in a gravitational interaction. So the amount of pull has to be the same. There's only one force there. It's the Earth-Sun gravitational interaction. Now, if it's exactly the same, you might say, okay, but the Earth is going around the sun is not going around the Earth. True, so how could it be the case that it's the same amount of force? Well, if you exert the same amount of force on the Earth, which is 1 million times smaller than the sun, and that exact same amount of force on the sun, which is 1 million times bigger than the Earth, then that force has a much bigger effect on the Earth, which is a much smaller object, than the exact same amount of force has on the sun. So there's lots of different examples that we could come up with, but the short version of the story is that whenever you have an interaction between two objects, the force that's experienced by the two objects is exactly the same, but in opposite directions. And that is a true fact. All right. I think that's all I want to tell you about Newton's third law. If you're wondering to yourself, wait, Newton's third law? What about Newton's first and second laws? We already talked about Newton's first law. I could remind you that Newton's first law, let me put that in these notes too. Why not? So this is a reminder. So Newton's first law is that objects, there's a lot of different ways you can say this. I'm going to say it like this right here. Objects experiencing balanced forces are at rest, or, and this is the tricky thing to understand about this one, or moving at a constant velocity. Right? If the force is, another way of saying this is, if there's any unbalanced force, well, that's going to change the motion of something. Unbalanced force, that's like tap, tap, tap with the broom on the bowling ball. Unbalanced forces are going to cause something to change its motion. If it's at rest, it's going to start moving. If it's already moving, then it's going to maybe speed up or slow down or change direction or something. Somehow its motion will change if the forces are unbalanced. If the forces are balanced, then its motion doesn't change. If it's at rest, then it's going to stay at rest. If it's moving, it's going to keep moving in exactly the same way. So imbalance causes change, and balance leaves things alone. If it's already at rest, stays at rest. Already moving, going to stay moving. So that's Newton's first law. What about Newton's second law? Never mind that for now. That is what we're going to take on in Unit 5. So you've heard of it before, I'm sure, but we'll get there when we get there. Okay, so that's that. Now I want to talk about how to put numbers on the force of gravity, to actually start getting some numbers into our force diagrams. So you know, most of the time we're going to be talking about, there might be a couple funny little problems that I throw at you where you're on the moon or something like that, but we're talking about the force of gravity on Earth. So this is not like some kind of universal thing. This is specific to like the surface of our planet. So how much gravity is there? And what do we measure force in? Force is measured. There's a lot of different units you can use for force, including pounds. But if you want the SI units, the units of force are newtons, after our boy Isaac, same guy with the 3 laws and all that. Force is measured in newtons. That is the SI unit, and we abbreviate that with a capital N. And looky right here, I've got a little spring scale that measures things in newtons. And it's a kind of scale, not that you stand on, but that you can hang things on here, and it'll measure how much force. And I don't know if you can see inside there, it literally is just a spring. So it really is a spring scale. And then it also measures in dynes, and looks like, I guess, 100,000 dynes is equal to 1 newton. That is not a unit that we're going to be interested in, so you can ignore that side. So we want to just figure out how much, if you have some kind of mass and you hang it on here, what's the scale going to read, and how do we actually figure this out? So what I have here, this is a little mass hanger, and I'm not sure if you can read on there. Somewhere on there, it's pretty dirty, is printed that this hanger is 50 grams. And if you don't want to take my word for it, then we could just come over here to our digital balance and turn that on. Get that plug out of the way. That's still in the way. Oh well. There we go. Yank it out of the wall. How about that? All right, so that's 0 grams right there. And, oh, I guess it's a little light, but close enough for us. So 49.9 grams. And, of course, grams are not the SI unit for mass. Kilograms are. So we got to think for a second. Maybe you can think for a second. What is 50 grams? What would that be if you converted it to kilograms? So this is my messy area of all my papers and stuff. Sorry. All right. So what would 50 grams be in kilograms? Got to move the decimal 3 places. Kilo is 1,000, so that would be 0.05 kilograms. 50 grams is 0.05 kilograms. Okay, how many newtons is it? How much gravity is there? Now, you might be, if you're really thinking carefully about all this, it looks like it's about half a newton. You might be thinking to yourself, okay, but you're not measuring the gravitational force here, Mr. McGrath. You are measuring the spring force. You're measuring like how much spring has to pull up to keep that balanced. But I would say to you that's the same as the gravitational force, because right now that 50-gram mass, it is at rest. It is just hanging there, not moving. What does that mean? It means the forces on it are balanced, which means that however much the spring is pulling up, which is half a Newton, the force of gravity must be exactly the same as that, balanced forces in the down direction. So how much gravity we got? We got half a Newton here. All right, so I'm just going to write that down real quick. Let me just replace that here. So for a mass in kilograms of 0.05, that's my 50 grams there, I got a gravitational force, which we measure in newtons, of half a Newton. All right, so let's pile some more on here. How about, let's see if you can see that. That's a 50. It's etched into there, another 50 grams. So if I put that on here, that's going to give me, that's a total of 100 grams now. And let's see what the scale says. Looks like we're at just about 1 Newton there. Okay, so that means that a mass of 100 grams is 0.1, right? We doubled that, and that was about 1 Newton there. I'm going to take here, this is a, you can see, oh, you can see that, I bet, yeah, right there, 100 grams etched on there. So I'm going to put that on the hanger, and go ahead and guess what you think. Let's see, if that's another 100 grams on there, now I have 200 grams total, which is 0.2 kilograms. And I'll take you up here so you can see the scale. And you guessed it, that's right about 2 newtons. So if you're not convinced by this pattern, we could just take it a couple steps further just to make sure that there's another 100 grams. I'm going to pile that. Oops. I'm just going to shake the whole thing there. And I'll show you here that now with a total of, if you're looking at that wondering how that adds up to 300, remember it's 50 for the hanger, and then I put another 50 on there, and then 2 100s. So that's a total of 300 grams. And where's my scale at? There it is. I get about 3 newtons. And you can keep going. I think I'm convinced. Hope you are too. So how do we, in general, how do you know how much gravitational force there is on something around here at the surface of our planet? You take the mass of it in kilograms. It's got to be in kilograms. And you multiply it by 10. And since this is in kilograms and we want to get newtons, that must be 10 newtons per kilogram. So the units come out right. Of course, when you're just using the numbers, you don't really have to think about those units all the time. But if you were going to think about those units, 10 newtons per kilogram, this is like the strength of the gravitational field around here at the surface of the planet Earth. How strong is gravity here? Well, you get 10 newtons of force per every kilogram of mass that you have. How much gravity? 10 newtons of force per kilogram. You got 100 kilograms, you're going to get 1,000 newtons of force. You got 10 kilograms, you're going to get 100 newtons of force, and so on. So that's how you do it. What does that mean? It means now, if we wanted to make a force diagram, let's make a force diagram of this. Right? So I will make my dot here. This is example is a 300-gram hanger on a spring scale. So what are the forces? Well, there's a force of gravity down, and that's a force of gravity on the hanger from the entire Earth. And then there's force up. I'm going to call that force of spring on the hanger from the spring scale. And it's just hanging there, not moving. So that means the forces must be balanced. And I can see, since it's 300 grams, and I just did this little experiment here, that 300 grams is the same as 0.3 kilograms. Multiply that by 10. That gives me 3 newtons. Of course, in this case, I could have just read that number right off the scale, right? It's 3 newtons. That's what the scale says. And since it's balanced, of course, that is the spring scale reading, so that is also 3 newtons. So what are we doing here? We're adding the ability now to be able to start to put some numbers into our force diagrams and actually know how much force there is. That is what we are at here. And the good news is, to put the force of gravity into any of your force diagrams, if you know the mass of the object, you just have to multiply it by 10. You need to be careful and make sure that your mass is in kilograms. It's pretty common for us to have to convert from grams to kilograms. That's a conversion. Move the decimal place 3. You need to be very comfortable doing that if you want to get the correct answers, of course. So there you go. There's your notes here, and the next assignment you're going to be able to start applying both of these ideas. So when you do that next assignment, which is called horse and cart, please have these notes nearby to you. There's stuff that you have to apply about Newton's third law, and there's stuff that you have to apply here, right, putting gravitational force in. I'll put up a video, of course, of me doing it, but give it the old high school try yourself. Have a great day.